So it then says that the body is pulled down a distance of 10 centimeters and released. Show that the ensuing motion will be simple harmonic motion. Find the time period and the maximum speed. So you can see here the natural length of the string is 0.6 meters. The extension due to gravity is 0.2 meters. Okay, so that's like sort of its natural equilibrium position, and then it's pulled down 0.1 meters. Now, simple harmonic motion is possible here, but you've got to be careful with a string. A string is different to a spring. Okay, you've got to make sure that this extra extension here is less than or equal to the initial extension. Okay, the initial stretch here, because if it was stretched further than 0.2 meters, if it was pulled down further than 0.2 meters, when it performs simple harmonic motion, it will go above the natural position. Okay, because if it was stretched more than 0.1, the amplitude would be more than 0.1. If it was stretched more than 0.2, the amplitude will be more than 0.2, and it will go back here above the natural. And what happens when it goes less than the natural is it doesn't compress. Because it's a string, it becomes slack, and SHM then won't occur. Okay, right? It'll stop. But this is good. This is all good because here it's only being stretched 0.1 meters. So SHM can perform. Okay, so that will be the center of oscillation, and it will go there, yeah, about 0.1 there, halfway. So the string will always be stretched. Okay, it will never become slack. So it will form SHM about E there, about O, and obviously the amplitude will be 0.1. So we can say, consider, as before, consider body moving in direction of increasing x. Now x is measured from the equilibrium, right? Okay, so applying Newton's second law, well, look at the forces acting there. You've got the weight pulling it down, take away the tension, and that will equal then to the mass, which we know is m, that's all we know, and then x double dot. Okay, so by Hooke's law then, T is equal to lambda x over L, while tension is equal to the lambda. Now we know lambda is equal to 3 mg, the modulus. Now the extension, if you think about it, it's 0.2 already extended from the natural position. We worked that out in the first video. Plus then this extra x. So 0.2 plus x. Okay, over then the natural length, which is 0.6. Okay, so if you do that, I mean, perhaps what we could do here is divide 3 by 0.6, you get 5 mg then. That might be a bit tidier. 3 divided by 0.6 is 5. Now let's sub it back in here. So mg minus, put the t in there, right? X double dot. So multiply that out. 5 mg times 0.2 is just mg. 5 mg times x is 5 mg, minus in front, of course. And what happens is, lovely, that these cancel. Okay, we'll always have a cancellation there. And then we just got this. Minus 5 mg is equal to mx double dot. The m's will cancel there. So x double dot is equal to minus 5g. Okay, so x double dot will equal to 5g. So 5 times 9.8, of course, is 49. I missed out the x there, haven't I? 5 mg times x. So minus 49x there, yeah, because 5g is 5 times 9.8, which is 49. So there you can see then we've got our omega, okay, from there, because it is of the form x double dot equals minus omega squared x. And we can say that motion is SHM because we're of that form where omega squared is equal to 49, which implies omega is equal to 7. Okay, so we'll sub it in. Okay, so t then will equal to, for the time period, 2 pi over omega, so 2 pi over 7 seconds. Okay, so we've got the time period. What else are they asking for? The maximum speed of the body. So the maximum speed, Vmax, remember, is equal to omega A. So omega is 7, and A is the amplitude. So the amplitude, remember, it was pulled down 0.1, so it's performing SHM there. So the amplitude is 0.1 meters. Okay, so we get 7 times 0.1, which is 0.7 meters per second. It'll be at its max speed at the center there of equilibrium.